Good evening, everyone. Welcome to the first week for the weekly interaction session for the NPTEL course, Dynamic Behavior of Materials. The NPTEL course code is NOC24ME102. I am Manay Shembekar, PMRF and PhD candidate in Aerospace Engineering, ISC Bengaluru. In this week, this is the outline for this particular session. So, in this week, we covered only like the starting points of the course. So basically, static deformation, dynamic deformation, the differences between those two, where dynamic deformation is important. So like a wide variety of applications. We'll be looking at two models just to recap, and then how the atomistic picture of a static deformation versus the atomic versus dynamic deformation looks like. Sorry. Okay, huh. So the at the very beginning we were like we recapped what static deformation basically is. So if you recall, suppose I have a beam like this and on which I am applying a force F on both ends. So the beam is already in static equilibrium, but if the rate at which the loading acts is very low, then you basically have a condition of quasi-static deformation. Yeah, I should write this quasi-static deformation. And because the applied applied loading rate is low, inertial effects are not existent or inertia effects are neglected. Further, we also see that if I take any two sections, say section A and section B, if I zoom into each of those sections, suppose A dash and B dash, this is my material, then both sections are in static equilibrium. So here, whatever loading section A dash experiences is same as section B dash. Oh, is so. But I think the first week content was pretty basic only. So okay, right, in quasi-static deformation. So as I was mentioning, all because the rate of loading is slow, each section experiences this. Every neighborhood, every small section experiences the same set of forces, which means that you could, in theory, analyze only take a few sections depending on what your geometry and material constraints do you have for your problem, and then from that infer your important properties. So, how many of you are aware of? I think because I assume that because this is usually a graduate level course, some of you would have at least heard or used about the universal testing machine. So here's a problem on the same. So it's, as you know, it's used primarily for quasi-static loading. So when we get something like a stress strain curve, you have a sample like this, then you apply clamp it on both ends, and then you apply some displacement to the displacement to the ends, and then measure the force. So you would get something like a stress strain curve. Say suppose this. From this, then you estimate different parameters, which include your Young's modulus E, which is the slope of stress versus strain in the linear region. And you also have your yield stress, where the linearity ends and then linear elastic nature of the material ends rather, and then plasticity begins. Then you would have something like a necking region somewhere here where the cross section becomes very small. That would, and then finally the material would fail. So UTM, like this is a very like the preliminary analysis that we do in a lot of undergraduate, say mechanical, civil, and I think even in aerospace labs. So I'm guessing that you are familiar with the UTM. And out of the tests that are given here, which of these do you think are not measured in UTM? Okay, so as I mentioned, you can do like quasi-static loading, so a compression test can be done there. As I've already drawn like a tensile sample, and we can also do a 3-point bending test. So the two tests basically no dynamic behavior is captured, especially high speed dynamics. So the high strain rate test and the shock wave test are the tests which cannot be performed using a UTM. As we go further, as we go further into the course, you'll be introduced. Sorry, you'll be introduced to the what's this?
Excuse me, sir.
Yes, yes. Go on.
You just mentioned that this is an undergraduate course, right?
No, no. I think this is a graduate level course because it already assumes
The
some amount of understanding of strength of materials and
the
like
course
stress strain.
says it is a postgraduate course. The course description
Mhm.
says it is a postgraduate.
Yes, yes. It is a postgraduate.
Okay.
Usually, in the first few lectures, you set up a few things, and then I think in the first week we haven't even introduced what are elastic waves as such. Like maybe you have looked at the atomistic perspective of how momentum transfer and inertia effects take into uh, basically move a disturbance ahead, which is what we call as a wave propagation in that solid. But you haven't really gotten into. I think elastic waves are in the second week's syllabus. So then after that you will go into plastic waves. Then a couple of weeks later, I think week 4 or 5, it's shock waves and so on and so forth. Okay. Another question on the quasi-static loading. So here we have been told that we have a quasi-static uniaxial tensile test of a material. Suppose X, Y, Z, and uniaxial tensile test. So force F is being applied along, say, Y direction. Quasi-static, so both ends will have the same load balancing it out, and each section will experience the same stress. So that is basically option C, and there is no jump in stress, or there is also no like stress propagation as such. It's a quasi-static system. So as we mentioned in the earlier itself, quasi-static testing. So everywhere you have the same stress for the uniaxial tensile test in the same material at a particular time. Okay. The next concept that we looked at in this week was dynamic deformation. So there were different perspectives to the same. So firstly, if we look at from a testing point of view, suppose I have a rod like this, then I'm pulling it say at a velocity v naught. That will in turn, and its initial length is L naught. then you essentially have a strain rate defined as epsilon naught is equal to V naught by L naught, provided like so as we are here assuming that the same velocity V naught acts for the given time at each of the ends, at both ends. If I then draw the plot of stress versus strain for uniaxial loading condition, so what I see is the flow stress begins beyond the yield point. I see a variation in instantaneous flow stress, and I also see a variation in the amount of ductility that is seen for the strain rate. So this is epsilon 1 dot, epsilon 2 dot, epsilon 3 dot, and here somewhere you have flow stress coming up, epsilon dot 3 greater than epsilon dot 2 greater than epsilon dot 1. Flow stress. If you remember, the definition of flow stress is basically instantaneous plastic stress. So again, simple, straightforward, following from like basic strength of materials courses and all. And you also see that as this epsilon dot increases, there is an increase in tensile ductility with increasing epsilon dot. So this is what we observe from like testing. There are a few resources I'll post a paper on experimental measurement of flow stress for different strain rates on the discussion forum. You guys can go through it and see how they measure the data, and basically it matches with whatever like the key outputs that we are seeing, that increase in tensile ductility and increase in flow rate with increasing strain rate. And we also saw that for a dynamic loading case, suppose I have a material like this and sigma is some stress sigma is applied, then for the quasi-static case, and this is the dynamic case, for the quasi-static case you see like a single crack going out throughout, which tells you about the phase, which is how we know the material fails, whereas for dynamic case crack branching is seen, and that branching depends on a particular criteria about how it only happens when for some at some velocity v greater than critical velocity for the crack propagation. So different kinds of failure mechanism arise both for tensile case as well as shear case, shear loading case, when we compare quasi-static to dynamic loading. And another thing is that here if I, as suppose I have a rod like this, fixed at one end, and the force F of t is applied. So if I look at some section A dash, section B dash, we now know that the stress states of the two cross sections can differ, which means there will be a time where section A dash is under stress, but BB dash isn't under stress, and then there may be some time later on when A dash has relaxed, but BB dash is under stress. This basically is like this is basically wave propagation, where the disturbance moves through the medium. So your applied disturbance moves through the medium, and what does this depend on? If you look at it from an atomistic perspective, so suppose this is a very simplified 2D model in reality, what you would have, suppose if you have like aluminum, then you would have like an FCC, which is space centered cubic arrangement of atoms. It's a complex 3D arrangement. I think part of this you would have perhaps covered in some mechanics of materials or some similar course in undergrad level. So this is say like aluminum FCC arrangement. In reality, when atoms, sorry, if you look at the microscopic picture of the material, when we apply a load, atoms would move around, but they would move around based on whatever crystallographic constraints exist. Like it may not be easy for the atoms to move in a particular direction where packing density is relatively higher. So those considerations will come up as you go in if you want to model it more closely. At a very basic level, if I want to see how disturbance would move, like suppose I have atoms like this and a force F is applied. After a while, what I see is at time t is equal to t1. Sorry, this is section A dash. There may be some contraction at A dash, but away from it, there may not be anything there yet. No disturbance may be seen. And if I see it at time t is equal to t2 greater than t1, time t is equal to 0, you may have a case where A dash basically A dash relaxes, or rather even undergoes some sort of rarefaction, and then BB dash is compressed. So how this disturbance moves ahead depends on, if you think about it, the mechanism of momentum transfer from particles to particle, from one particle to the next particle. And that in turn would depend on what sort of stiffness the bond of the two particles have, what masses those two particles have. Suppose the particles are very light, then you can expect the applied loading to move ahead very quickly, because one particle will move very freely, have very less inertial uh, component, and it will move very freely quickly to its neighborhood and so on and so forth. If the particles are massive, because of the inertia, those particles will propagate the disturbance in a slower manner. Flip this around, think about stiffness. Greater the stiffness, more easily the disturbance will pass around, more quickly it would pass around. So normally there is a speed, characteristic wave speed, which depends on, which is basically a function of some sort of stiffness and some sort of inertia measure. This is a very crude, very simplistic way to think about this. As we go deeper into elastic waves and all, you'll see how whatever we are talking about makes much more sense. With this overall understanding of dynamic deformation, we'll quickly look at a few problems. So now suppose you have a material which is under a high strain rate, so epsilon dot 2 comma epsilon dot 1, where epsilon dot 2 is greater than epsilon dot 1, and then we are asked about what happens to the material. So as we have already seen, if I draw the uniaxial stress strain curve, something like this would happen to epsilon dot 2, and this is for epsilon dot 1. So we know that the tensile ductility should increase, and we also know that the flow stress would be higher. So here we have, I think only option B, flow stress higher. Again, Young's modulus is unchanged in the linear elastic region. Both of them are overlapping, so there's no There's no change there as such. Okay. Another question that we have is that not changed. Okay. Yeah.
There is one
Hmm.
question. Where there is
Yes.
one question in my mind.
Yes.
Can you just stand up for few seconds to the last problem you have discussed?
Last problem is this one.
Yeah.
Hmm.
So, if I am talking about the flow stress,
Hmm.
definitely it increases. It seems increases. But if I am talking about the tangent modulus, so is there any surety that always, in the case of metals, tangent modulus should be decreased, or some in some loading cases it can be increased, or whatever it is?
Right. Okay. So I do not. I actually don't know the exact answer. My guess is that because the flow stress is increasing as compared
Mhm.
to say a lower strain rate value, we would
Mm.
expect the tangent modulus to be higher.
But after observing this curve, I think as far as we increase the loading, this
Hmm.
tangent modulus value just seems to be decreased. Okay, okay, okay.
Okay, let me get back to you on that. I think I'll also check on it. So sorry,
Sir,
I can't really.
sir, most
Yeah.
of the time
Hmm.
we design things such that they are well below the yield point
Hmm.
with a good factor of safety.
Hmm.
So, why is it this dynamics of structures study is required? You see, you have drawn one vertical line. You move towards left, where
Hmm.
the yield point
Hmm.
maybe we are well below that limit
Hmm.
when we are designing.
Hmm.
So why at all we need to come and choose a point where you have drawn the vertical line.
So think about it in this way, right? Everything has its own like just as everything has its own characteristics, that in turn decides what sort of differential advantage that characteristic or differential disadvantage that characteristic would have. When you are, say, designing a component which is well below the yield point, you already expect the material to not say, or even if it deforms, to be deforming well below the yield limit. But suppose you are looking at, say, like an aerospace application where factor of safety is very small. If there something goes a little bit above or beyond, you already need an understanding of what might happen. Or imagine like you are designing a car, right? Tata cars recently are getting very high safety ratings, so for their crash worthiness. So that is where this sort of knowledge will come into hand. That if very rapid loading happens or a projectile hits, if I think it's in the second lecture of the this week. If you, I would suggest you to just recap it a bit. Professor has gone through a lot of civilian as well as military applications. But even better than that would be if you could get your hands on on the Mark Mayer's textbook. He has really like I can't show it here because of copyright purposes, but he has really shown
Yes.
a nice number of diagrams how things work out.
Okay, sir. Okay.
Any more doubts with this, or if not, I'll move ahead.
You can move.
Okay, so what what are the important characteristics in dynamic deformation. So as we have already talked about it, inertia forces are necessary, and we also have stress propagating as waves in the material. So like whatever disturbance that we apply, that will cause some stress, which will cause the material to move ahead. Atomic vibration that you are seeing here is basically underlying any material which has a non-zero, like above absolute zero temperature. Any such material, if you look at it microscopically, there will be some sort of atomic vibration that would that would help us get a picture of what is happening, whether we apply a quasi-static or a dynamic deformation. But like the key characteristics from a continuum point of view would be consideration of inertia and wave propagation being observed in the material. Okay. And the next problem is on sound wave velocity in a material. So as we discussed earlier, if you look at it from an atomic, from a very particle perspective, there is momentum wave propagation would, or a motion of disturbance would go from one particle to another and so on and so forth. That would depend on how light a particle is. So some sort of inertia effect, inertia measure. It would also depend on what sort of stiffness there exists between the two particles. So a stiffness measure. Right. So for our case, yeah, for in this case, the stiffness measure for elastic waves, it would be at least Young's modulus. And again, sticking to elastic waves, you will have density as the inertia measure. As we move further into the course, you'll encounter shock waves where there is under certain conditions, large hydrostatic pressure would be acting on the material, causing it to, in a sense, flow, which causes changes in density as well. So that is little ahead. For now, for the sound wave purposes, we'll basically have an elastic wave propagation. So stiffness measure and inertia measure, which is Young's modulus and density. Okay. The next question is, uh, okay, uh, I think I'm a little confused. Has split Hopkinson bar been taught, or I think it's not taught in the first week? I think. Just a second. Oh, no, it's taught. Okay. Okay. So split Hopkinson bar. I'll just draw a schematic. You have a gas gun which connects to a striker bar. There is an incident bar. There is a specimen, and then there's a transmission bar, and at the end there is a shock absorber or momentum capture. This is my incident bar. This is my transmission bar. This is my specimen, and here somewhere here I think you have two strain gauges to measure like how strain changes with time at the different at different instances. And if I look at stress strain curve, what I obtain is something like this is for given epsilon naught. Okay, this noisiness that comes again will be explained in the coming lectures. I think third week or something is there. So, and what basically happens is the gas gun would, this is the striker bar. Gas gun would fire the striker bar, which in turn hits the incident bar, from which disturbance is propagated to the specimen and then out to transmission bar, and rest is taken away by the shock absorber. Okay. With this we can, so this setup that you are seeing here is for the split Hopkinson bar, pressure bar. This is also called as the Kolsky bar. Kolsky bar. And this particular setup is for compressive loading. There are other uh, setups, slightly more complicated, for tensile as well as torsion loading, from which you can obtain a series of stress strain curves for different strain rates. So we'll be learning more about this in detail, how stress wave propagates plastic elastic stress waves, then the different fronts, how they go through the specimen, and then how do we measure it. Right. So from in this, it's a very simple numerical example, but I think it would have been better placed later on in the course. Here we are basically trying to estimate what sort of strain rate uh, we are conducting this experiment for. So here we are told that there is a specimen length L naught is equal to 6 mm, and then the striker bar will hit the incident at 12 meter per second. So like 6 mm, it hits at 12 meter per second on the incident bar. Right. So the way we like simple calculation, the way we do it, this strain rate calculation is speed of the striker bar divided by its length. So that turns out to be 12 upon 6 into 10 raised to minus 3, which is nothing but 2000. Option D. There's one more, like we'll study this again later on, that how when the striker bar hits, when the striker bar hits the incident bar, a pulse would be going into the incident bar, and another pulse would simultaneously propagate in the striker bar. So at contact, one stress pulse would go this way, another stress pulse would go this way, whereas this would be moving at say V naught, and then after when these two meet, you essentially get a release wave. From that, we can estimate that the wavelength of the elastic wave which would propagate into the incident bar and then the specimen and so on, it generally turns out to be twice of the length of the striker bar. Okay. I think that would be more confusing right now. So
This
just mm,
strain rate that you have derived from this formula,
mm.
is it the strain rate at the early stage of this dynamic deformation, or we can consider this as the average of the time interval?
We can consider it as average for the entire measurement.
Okay. Okay.
Okay. Yeah. So as someone asked a little while ago, why are we interested in studying? So there are a lot of civilian as well as military applications I'll first go to the military one because I think those are easier to visualize. So suppose you have a bullet being or some sort of projectile attacking a target, right? In this case, what would you be interested in? If you are the one who's firing the projectile, then you are interested in say how much the bullet penetrates this target. If suppose you are the target defending some important uh, equipment or something like that, then you are interested in stopping say the penetration or stopping the amount of energy being transferred into the target. So military wise speaking, there are both armor. So this I think this side would be target side would be armor and the projectile side would be anti-armor applications. So what would be armor applications? It would be say like something like body armor to protect soldiers and all, which could be like the simplest example is a bulletproof vest. We also have armored vehicles. Again, simplest example of the top of my mind could be a tank. Flip this around, what would an anti-armor be? An anti-armor would be a projectile which penetrates using some mechanism. So you could have something called as a kinetic energy penetrator. What is kinetic energy? Sorry. What is kinetic energy penetrator? You have like a very heavy metal rod like tungsten, and it is of a considerable size, and then you launch it at sufficiently high speeds so that it can transfer that very high kinetic energy into the armor material in an attempt to break it. There is also something very popular called as the shaped charge. Shaped charge has like say a sensor, then a high energy, sorry, a detonator, and then you have some sort of explosive lining. This is the sensor S, this is explosive. When the sensor touches the target, when the sensor touches the target, it activates the detonator, which in turn fires up the explosive. This creates a very sharp needle-like projectile coming out of the shape charge. This has much better penetration into the target. There are other variations of this, including like a disc, which has, I think, which is called the explosively forged projectile, if I recall it correctly. On the civilian side, you can think of if you recall a bit of manufacturing, supposing some of you have seen studied like a manufacturing subject in your undergrad, you can remember that for two metals to be welded, their melting points need to be close by. So we can do something called as an explosive welding, which bypasses this requirement. So an explosive welding, suppose this is my cladding. Here I place some explosive and then I detonate, and this is my base plate. So once I uh, once I detonate this, you can quickly join to very large surfaces, and you this can also bypass that requirement of close melting points. So this could be one. Another is something called as explosive forming, wherein suppose you like have like a workpiece which is a metal sheet, and then this okay, you have like a metal sheet, then this is suppose my die, and this takes it away to vacuum. You could have like water or some other transfer medium, for shock transfer, and then on the top, some at a little distance away, you have like a high energy explosive being detonated. So this would create shock waves, which would transfer through the medium, and this is my metal worksheet, which basically gets formed according to my die. You can also do consolidation, so like converting graphite to diamond, graphite powder to diamond based on like suppose this is my powder and this dashed area is my explosive. This sort of shock consolidation can be done to a powder. This is used in say like uh, diamond cutting tools and all, converting graphite to that. Okay, this is a very brief list thing. You can go like a long way with this. As I mentioned, like crash worthiness in cars. You could also think of like satellites in space which are being impacted by very microscopic debris. Even that causes a big dent. So if we can study how dynamic deformation happens in response to say like a very small loading, quick sharp loading, then we can use those insights to then transfer that learning and engineer our say satellite in that particular way. So wherever you see like a sudden change in loading, or like think of it like force as a function of time, if it's changing rapidly, then that is where you could apply this. This includes both elastic, plastic, and at the very top even shock waves in the material. And this has a very intimate relation with how the microstructure of the material is. So one of the very interesting research that we are doing in our labs is one of my seniors is studying how microstructure affects wave propagation for like for high frequency waves. So with that, if we like from the results that he has been able to show, we have been able to we have been able to tell what sort of microstructure we should have so that we disperse a wave quickly, which could be coming off say from like a projectile impact happening on a structure. So suppose a projectile hits on the structure, then what sort of microstructure should be inside that structure to quickly dissipate that wave so that none of the energy transfer goes into the critical parts of the structure, whatever. So very wide applications, and I think as you go more and more into the course, you'll realize that if you look around a bit, it has like it's very well structured and widely usable. Okay, what was okay? So the a few problems on the same. So the first, this problem basically asks us about which of the following entities are used in armor applications. So as I mentioned, armor would be protecting a target from a projectile P. So that would be say like a bulletproof vest and a bulletproof vehicle. Okay, which of the following is not an application of dynamic behavior of material? So, okay, the first is an impact of a small meteorite hitting the earth. So you can see that this would be a dynamic deformation example. Bomb blast that hits a building. Again, I think this is perhaps not a correct option, but okay. Like some detonation happens, shockwave goes through the ground, and then it, as well as through the air, and then it hits the building. That is another dynamic deformation. As I mentioned, vehicle crash. So it's also one. So as you go more and more into As you rather start looking more and more in your everyday life, you should be able to see a lot of applications. Okay. Next up, I'll cover one. I'll cover a couple of analysis that are usually associated with any of these courses. So the first one is vibrating string. I believe it has been taught in the class, I think second, third or fourth lecture, but we'll just quickly recap it. Suppose this is my string, this is my origin y, x. If I take a very small section of the string, a, b, and then right angle triangle c, I think I should first write my assumptions. Any of you play a string instrument like guitar, ukulele, or I think veena or something? Okay, so some analysis like this could be like a good starting point there. If I look at the very small section of string, the string A, B, C, because you have assumed like a constant tension throughout the string condition, I'll show this to my T, theta B, theta A. This is also HP plus T theta A. Right. So if I apply Newton's second law of motion, I have summation Fy is equal to m into Ay, summation Fx equal to 0. So there is no lateral net movement of the string. There is only perpendicular movement, a transverse string. So mass into Ay. If I assume density of the string to be rho and segment per unit length and ds as the length. So rho ds would be my mass which would feed into m, and my Ay would be nothing but second derivative of y, vertical displacement with respect to time. So if I write down, I have t sine theta b minus t sine theta a is equal to rho ds t square y by dt square. If I further simplify this, this is sine of theta a plus d theta minus sine of theta a divided by d theta multiplied by d theta t rho ds tau square y by dot t square. This can be approximated to be the first derivative of sine of theta, which is cos of theta assuming like this string is infinitesimal, and that would give you d theta to be also infinitesimal. So you have something like t cos theta d theta equal to rho ds plus square y by dot t square. We also know that tan of theta nothing but y plus ty minus y upon x plus dx minus x. So this is coming from segment. This is x plus dx. Then if I do this is y, this is y plus d. dy can be approximated to y plus dy by dx is y by x plus bx. This basically ignores order of dx square terms, which is a good, which is a valid approximation provided that we are already looking at infinitesimals. So you have tan theta I to be of theta I, where approximately partial derivative of y with respect to x, and then if you take dou tan theta I by dou x, dou square y by dou x square. It's nothing but sec square theta I dou theta by dou x. Differentiating this. So moving around, you get dou theta to be cos square theta I dou square y by dou x square dx. This is my d theta I, and if I use this my earlier equation, another important thing is cos of theta I is dx by ds, which means ds is equal to dx by cos theta I. If I combine these three equations, I end up with t cos to the power 4 theta I is equal to, no, into, sorry, t square y by dx square is equal to rho dou square y by dou t square. If we if we assume very small oscillations, you have cos of theta I tending to 1, which gives us rho dou square y by dou t square is equal to t dou square y by dou x square. From this, you can estimate the characteristic wave speed to be root of t by rho. So a stiffness measure and an inertia measure. So every this is a good habit to check. Anytime you end up getting a differential equation, partial differential equation, you should have, for wave propagation, you should have like a stiffness measure and an inertia measure from which you can determine the characteristic wave speed. The next example I have is of a helical string. Sorry. So on so forth. Okay, so here this is a different. Here we apply loading F that would cause, after some time it would cause, say, compression, and then the other parts are still relaxed. T is equal to T1. After another time you'll have a relaxation followed by a compression, and then other parts are still normal, so on and so forth. Okay, for the helical string, uh, we'll have a few assumptions. Again, some assumptions: uniform cross section and material. I think I should have written this with this earlier also string. Then you have a thin cross section. So if I analyze how force would act in a helical, in a spring, suppose I have a spring like this. We know that with two ends U1 and U2, as with the ends 1 and 2 displaced by displacements u1 and u2. We know that the force is k times delta u, k times u2 minus u1. If I what we are interested in is how this u2 minus u2 and u1 change with respect to their original positions and not what their actual values are. Suppose if I have the spring length initial as L naught, I can write it K L naught u2 minus u1 upon L naught. So the relative displacement between the 2 points is what we are interested in. If we transfer this to a like a long helical spring, we can rewrite the force at a particular cross section or at a thin cross section. We can rewrite the force as change in relative displacements at this particular cross section. Suppose S denotes displacement as a function of the location of spring, then the force at cross section A dash would be say K times relative change of displacement just before and after the cross section force at A dash. And if I now, for simplification, I'll just draw it as a thick circular line with dotted string parts. If I now look at a cross section at a distance dx ahead of say A dash, BB dash, what I see is at this end A dash the force is Fa, this end the force is Fb. Fb is Fa plus df, and Fa is nothing but k times ds by dx. Fb is k times ds by dx at b, at A, at b, which is nothing but ds by dx at A plus dx times ds by dx d by dx of dx by dx into dx at A again. So this is a second order, like a first order approximation for the infinitesimal cross section. So this cross section is a, like, I'm just writing it in quotes. It's not how normally see it, but from this we can determine the net force summation Fx is equal to Fb Fa, should be Fb minus Fa, which is k times ds by dx plus d by dx of ds by dx minus k times ds by dx to dx, which is basically d square s by dx square into k into dx. This is the net force, and if I look at the net summation fx, which is mass into ax, mass is mass per unit length, into length of the cross of the thin section, which is dx, into d square s by dt square. It's the acceleration, which is nothing but k times d square s by dx square dx. So this
Here,
should be
here you have taken the S as the a parameter which indicates the distance between.
Displacement at a particular cross section.
Okay, okay, okay.
And basically, if I move this around, I should get something of the form k times square x by dou x is equal to rho times square x dou t square. So another stiffness measure, another inertia measure. So from this you can get k by rho to be your wave speed, root of k by. Okay, okay. I think this is the set of examples and what basics I had to cover for. I think it's first week only, so we'll have more content as we move forward, both in terms of examples as well as few interesting problems or derivations that I might find. Do you guys have any other doubts apart from either like what we have discussed today or what has been taught in this week's lectures? If not, then we'll call it a day. Okay, thank you all for attending, and we'll meet
Vinay,
again for
shall
the.
we
Uh,
get the any document regarding what you have discussed today?
yes, I'll be uploading this PDF as well as a recording of this lecture
Okay,
on the. I think you should be seeing that in the NPTEL webpage itself.
okay.
So this PDF of this PPT will be uploaded. You can be, I think by tomorrow I'll just sort it all out. I have to edit out a few things
Okay,
as you saw. So
okay.
once that all is done, by tomorrow evening maximum, you should be able to have everything online.
Okay.
Okay. Uh, okay then. We'll meet again next week. Thank you for your participation. It's interesting for me as well, and I hope to see you again in the next
And next discussion, which day I can expect?
discussion. So the way this works is every this sort of live interaction, discussion, and so on will occur on Friday
Okay,
at the same time, 7 p.m. Between
okay,
7 maximum till 9 o'clock,
okay,
depending on
okay,
how many
okay,
concepts we have to discuss.
okay, okay. Thank
The
you.
format will roughly be the same. We'll be going through a few concepts and we'll be going through a few problems.
Thank you.
Okay then. Thank you.
Thank you, sir.
Thank you.